All right, here's another vector addition problem. This one I'm going to go straight into components methods because this one's not very symmetric. It has vector A that has magnitude 3 and is directed towards standard angle of 75 degrees. And vector B has magnitude 5 and is directed towards standard angle of 25 degrees. And the rest of the question is pretty much the same as the last couple at least that we have done. So like I said, I'd like to jump straight into just getting my components set up so I can do the addition. So I'm going to start out by saying what is a sub x, and then I'm going to do a sub y, and so on and so forth. And so for a sub x, the formula again was a times cosine of the angle for a, which in this case means I'm going to be doing 3 multiplied by the cosine of 75 degrees. And if I put that into my calculator, I get, I'm just going to report some of the numbers here, 0.776. Let's see, we're working at, I don't know, maybe 4 or 6 figs is good enough here. So 6.5 it would round off to. When I did this, I actually kept unrounded numbers as I went through the calculations. I'm just going to report rounded numbers, so maybe there might be some round off issues, but it'll hopefully be reasonably close in the final answer. I just don't have enough space on this whiteboard region to write all the numbers out that I had on my calculator screen. So for the y component, I'm going to do a sine of the angle for a, so that's going to look like 3, oops, don't mix up your sines and your cosines, right? My hand wasn't listening to my brain there. It sometimes happens. I don't know if anyone else ever has that experience. But 3 sine of 75 degrees, I put that into my calculator, and I got 2.89 and a whole string of sevens, like 4 sevens and then 479. But let me see. I'm just going to write down 8, 9, and how many more do we need? Maybe just I'll round off there to 8. That's 4 sig figs, which I said was my standard. Okay. And then similarly for b, so b sub x is going to be equal to b cosine theta b, which is going to in this case be equal to 5 cosine of 25 degrees. I'm putting all that into my calculator. I get, again, rounded off, I'll stick with 4 sig figs, 4.532, I guess it's going to turn out. That was kind of close there because it's 5315 and so on, but I'll just make it a 532 right there. And b sub y in turn is going to be b sine of theta b. You know, I really hope that these kinds of problems are the most tedious problems we face all semester long, and I actually think they very well might be. This is a part of this course that I sometimes dread having to go through, so if you're dreading this a little bit, I feel your pain, and hopefully you feel mine. But just recognize that one of the things we're practicing here as we do this, and I'm just going to copy down that I've got 2.113 here for this, is even the most tedious and painful problem, if you structure it neatly and if you structure it well and then you're attentive to details and try not to make mistakes, it's really not that hard to get to correct results. So now if I want to say like, okay, what is d sub x going to be? Since I have a sub x and b sub x and I know that d is equal to a plus b, I'm just going to add up those two numbers. So in this case, that's going to mean I'm going to add like 0.7765 that I have there. That's for the a sub x, plus the 4.532. And I used, when I did this myself before doing this video, I didn't round off quite as much, and the result that I have written down for this is going to round off to, so there may be some round off error in this, but I'm not going to worry about it too. But it would be close to 5.308, at least is what I like, 5.307999607, more precisely based on unrounded numbers. D sub y in a similar fashion, we're going to add up this one and this one. So 2.898 plus 2.113, and again, I know this is tedious. And let me see, it looks like the unrounded, or the rounded version of d sub y should be something like 5.011. The unrounded had like a 10868788. In case you're curious or want to check what you had on your calculator screen, that's what I had without any rounding. Hopefully that all kind of makes sense I mean, these were all rounded numbers, so again, there might be in that last digit, there may be some uncertainty there. And then, so I've got those numbers to calculate. I'm being asked to find the magnitude. So this is a lot of work because I have to go from magnitude angle into components, add the components, and then now I got to go back to magnitude angle again. So it's reasonably straightforward. It's easy to get lost. So just recognize like being kind of organized about this is really the big secret, and recognizing kind of like, what am I doing when? Like, what is the goal for each part? And I'm writing a square root here because I want to now add these guys in quadrature, and I maybe need to leave more space for that. So 5.308 squared plus 5.011 squared would be the rounded off versions. And again, I did it in my calculator where I had the liberty of not having to round off. But on this screen, boy, there really is enough space. So I think, let me see. This is kind of a final answer here. Maybe 2 sig figs is good enough. I have like 7.2995, etc. But I think I can just round this off now to 7.3. I like to round off a bit more as I get closer to a final answer, just to remove any round off error that may have happened there, even if I had been rounding off as much as I've shown here. But again, on my calculator, I did a bit less. Maybe because I'm just that fastidious about being exact. How do you do the angle? So usually the maneuver that you always want to do, I think at least, I usually do this. Maybe there's other ways. I mean, you can analyze the right triangle, but the formula we had involved just taking a tangent inverse of the ratio, and it was always y over x. So, with rounded numbers, and this is where the rounding may cause more of a difference, because again, in my calculator, I entered the unrounding values corresponding to these two, the unrounded values, that is. And then my calculator spit out like 43.350, etc. But maybe I can just round that off. I think it's said to do this to the 10th place. So if I didn't have too much, and sometimes you may have like that last digit, you may have a slight round off error. But I think mine is coming to 43.4 degrees for that. And I always have to ask that question here because remember there's this whole story about principal value and inverse functions. Is this the correct one? But in this case, I don't know, maybe I should draw a picture of this, but I think it makes sense. Actually, I don't think I need a picture, come to think of it, because I could draw a picture of the whole vector addition and kind of say like, well, what quadrant was it in? But you know what? I've got the components for vector D, and it's pretty clear that this is in quadrant 1, and so therefore it's no problem. I know this is going to be the correct angle. It's usually when it's in quadrant 2 or 3 that issues start to come up, because the tangent inverse only gives you values in quadrants 1 and 4. So if you know you're not in those two quadrants, you got to maybe add 180 to whatever angle you get. Anyways, let's check and see if we got it. It looks like we did.